tomorrow, we're going to focus on a different topic that, while it is a function, is a very different type of relationship than what we've looked at. We've been working with graphs and finding the slope and calculating the slope and writing equations. Today, we're going to focus on a different type of relationship. We're going to use this example to kind of learn it. So each graph here shows distance as a function of time. One graph shows the function when Mr. Dilla is driving in his neighborhood. The other graph represents driving on major city streets, and the other graph represents Mr. Dilla driving on a highway. We're going to figure out which graph matches which scenario, and we're going to go into a discussion on how we're figuring out those values so that we can look at a graph and determine the situation. So let's just talk about roads. If you were thinking about a major highway in this area, what roads come to mind for a major highway?
By Route 9.
Route 9, okay, Route 9, Route 70, maybe. Any others?
Parkway.
Yeah, the Parkway is probably a really good example. The Parkway or the New Jersey Turnpike.
Yeah.
Think about how fast people drive on, like, the Parkway.
Like 60.
Yeah.
70.
Okay, how about city streets? What do you think of, like, in this area when you think of a city street?
25.
30 miles
Yeah, like
an hour.
30.
Like downtown.
40.
Like what roads? A city street.
Like downtown.
Downtown? Like
15 miles an hour.
Like
Slow.
Squawka.
Like
Squawka, okay, yeah. County line, maybe even New Hampshire.
Yeah.
Those that go out that way. How about neighborhood driving? What do you think of?
5 miles. Neighborhood driving.
5.
Like
19? That's the
Joda,
exact
like
number.
when you go
Yeah.
to that place.
75.
Maybe a little bit slower,
Yeah.
right? Think about like Woodlake. If you're driving in Woodlake, there's a different speed limit than there would be on Route 70.
Yeah.
Okay, so think about that as we go through here. Let's find the slope. Can we find the slope of each graph?
Yeah.
Yes. How do I find the slope of each graph? What do I do? Or what do I do to find the slope of any line?
MX plus B.
Okay, so we have that equation, y equals mx plus b. Okay, that is the equation that represents a line. And how do I find the slope? The change in y over the change in x. So what do I need to determine the slope of any one of those lines? How am I going to find the change in y over the change in x? Or some of you have said the rise over the run. How am I going to find those values?
Well, it goes 1, 2, 3, 4, and then it goes 40. So, can we make another point?
You can. Where would you?
The first one, the 130. Can we do 2?
Is there another point you know besides going to 2 hours?
Yeah, right there. 4, 120. Oh, well, 0, 0.
We can use the origin here. Yeah, all three of these lines go through the origin. Okay, so we can figure out our slope. How would we identify our slope?
By seeing the
Oh, wait, never mind.
because when we go from 0, we go over 1, but then we go up 30.
Okay, so we're going, our rise would be
30.
30,
Yeah.
and our run is
1.
1.
Wait, you rise one and you go.
No.
Oh.
0.
Oh.
So our change in y here, this first coordinate was 0, 0.
Yeah.
So we went from a y value of 0 to a y value of 30, which would be here, my positive 30. And then an x value of 0 to an x value of 1, which would be our positive 1. How would we find the slope of graph B? Or what is the slope of graph B? Yeah, I'm rising 40, running 1. For every 1 x I'm advancing there, I'm increasing by 40. How about the slope of graph C?
60 over 1.
Good, 60 over 1. What does the slope represent in these? Let's add some context to that number. What does the slope represent in all of these? What is that?
How far you go in the amount of time.
Okay, so it's how far you go in an amount of time. What do we call that when we're driving?
Miles per hour.
Yeah, miles per hour. So we have graph A, graph B, and graph C. We know the miles per hour. Okay, so now just look at the graphs themselves, the lines. Which graph is the least steep? The least steep.
Hey.
What do you think
These steep.
The slope is what?
It's small.
Yeah, its slope is kind of small. Think about how the line is moving. Like it's kind of flat. Which line is the steepest?
The
C.
C.
See, yeah, this is definitely the steepest. And notice what it means to be a steep line. Right, the line's kind of shooting up. Its slope is a bit higher than the slope of the other one. And then graph B is like kind of right in the middle. So now, very quickly, and I don't even know if we'll time this, but take a look at the three graphs. Can you, with the people that you're sitting with, identify which graph represents highway driving, which graph represents neighborhood driving, and which graph represents driving on city streets? If you had to sort them, which one do you think, as a group, would relate to each graph? Take about a minute, figure out where we would put them.
Neighborhood, city, street. Wait, neighborhood.
So city streets, neighborhood, and highway.
Neighborhood. City. But in cities, you can go in mad.
Wait, we didn't start. What do you mean you don't know?
So do we feel like we could sort these?
Yeah.
All right, who wants to give me one?
I do.
Jordan, give me one.
Highway.
Highway.
For C.
First. Okay, who else wants to?
This is like Jeopardy, like highway for $300.
Or like,
Neighborhood for graph A.
and then do we think city streets for B?
Yes.
Yeah, which that makes sense. In a neighborhood, you would drive slower. I'd argue maybe even slower than 30. I think Woodlake's probably 15.
Yeah. And then the highway faster than 60.
Some highways are 55. The Parkway, for example, in some sections is 55 miles an hour. In some sections it's 65. Some highways in West Virginia are 75. Right, so it does depend. But this is a pretty good indicator of where we'd be. Okay, so now we've identified these linear relationships, these three. Okay, so now let's take a look at this. We're actually going to do that. So this graph here, this graph represents Mr. Dilla's drive to work. You're going to write what's in red down. This is a qualitative graph. This is considered qualitative because it describes a function visually, please, not with numbers. And as you write that sentence down, that definition, take a look at the graph itself. Yes, my x and my y-axis are labeled. However, besides that, there are no numbers on my graph. I don't know if that time is represented in minutes, in hours, or in 30-minute chunks. I also don't know if the distance in miles, I don't know if each unit on that graph is 1 mile, or if it represents 5 miles, or if it represents 15 miles. I know that the time is in hours, and I know that the distance is in miles, but I don't have specific values. That's not what qualitative graphs are about. Qualitative graphs are really about a situation. Now, section A, section B, and section C are actually taken from the previous slide. Those are the lines that we already found the slopes of. We know that section A was that 30-mile-an-hour section, and that section B was the 40, and that section C was the 60. So we're kind of putting all of them together.
So this is a graph of all graphs?
Yeah, it's a graph of graphs.
It's like the
So
mother
Mr.
graph?
Dilla's driving. What's happening? What's happening? Explain. Let's add. We're almost going to add a story to Mr. Dilla's driving experience. What happened when Mr. Dilla started to drive?
He started slow.
Sandra Lopez to the main office, please.
So he was slowly driving where?
Wait, he's in a neighborhood right
He's in the neighborhood, yeah.
to Wawa, to the streets by Wawa. No, ShopRite. No, not the ShopRite.
Oh my
The gourmet glass.
Starbucks.
Well, he's driving to work, so we will add context in more detail later. But what we need to focus on right now are those two little sections that I did not mark in red that are horizontal. What do they represent?
The bridge.
Transition between them.
Okay, so yes, transition absolutely, but think about the graph. What's happening if you're envisioning Mr. Dilla's drive to work? What's happening during those two
Stop.
horizontal sections of the graph?
He moves even slower.
Is he moving slower?
He's like starting to, like, he's kind of like,
He's like braking and
Like-
like stopping.
no, like starting, like, because he's not stopping. It's like a constant, like the gradual.
But he's like
Because he's
sitting
obviously
there.
changing.
He's sitting there. He's
This is
sitting
like,
at the
oh my god,
stoplight.
I got it. You know
He's
those
at the
parts where you
stoplight.
go and then you have to do the turn and then all of a sudden you're on the.
Oh, like a jog handle?
Yeah, that.
So here's some of you are saying one thing and some of you are saying the other. Some of you are saying he's slowing down or he's braking. And then others are saying he's at a red light.
Yeah.
I don't
What's the difference? Let's talk about what is going on in the graph. We don't know numbers, but we know two things. We know the x-axis represents time, good. And the y-axis represents what?
Distance.
Distance. Okay. So in that horizontal section, what is changing?
like the speed,
That's
the constant, like
the time.
Time is passing.
He's at the stoplight.
Time is passing, but what is not changing?
no time.
The distance.
We're only comparing two things. We're comparing time
Oh
and
my
distance.
god.
The time is passing, but no distance. He has driven no farther because his distance hasn't changed. So what must be happening here?
He had a stoplight.
We don't need context yet, but what do you know about his driving experience? What's happening at those two moments? He is stopped. If he was slow, what would the line look like?
It would be going up.
It would still be going up because he'd still be driving distance. So this would be a stop. And you can add you can add a little bit of context now because we know Mr. Dilla starts driving. Where does he start driving first? Where is he driving here?
Neighborhood.
Mr. Dilla's driving in his neighborhood, and then what?
And then he turns right into the intersection.
We have a horizontal.
He stops.
Why?
He's at a
Because
stop
now
sign.
he's I don't know how to say it.
He stopped.
At a stop sign.
Okay, he's at a stop sign. He stopped at
Okay.
the stop sign, and he turned onto.
County line. And he went
Okay, he turned on the county line. He's driving down county line,
back.
and then what happens?
He stops.
He stops
again.
He
And
stops
goes
again.
to
Why
red
does he
light.
stop now?
Red light.
Over.
Maybe he got pulled over. Maybe stopped for ice cream on
Red
his way.
light.
And then he's on a police chase. So he goes here.
Maybe not a police chase, but you're getting the idea. He stopped again.
He needed to use the bathroom.
Yeah. Stopped for gasoline, stopped for coffee, used the bathroom. There's so many reasons why someone would stop. He stopped, and then what happened?
He ran
He
over
went
the
faster.
Quiet down. And then he got on the highway. So we're putting together all the factors of this qualitative graph. The key here, and this is what happens all the time, a lot of students see that horizontal and they think he's still moving, and maybe at a constant rate. You just see that straight line. Think about this. You're always comparing two values, right? You're comparing your x of time, your x-axis, time is passing, but the distance didn't change. Those two axes are extremely important when you're working with qualitative graphs. What do you think of when you think about qualitative versus quantitative?
I think of
Quality versus quantity.
Yeah, quality versus quantity is a big one. The most important thing here is that we know that our qualitative graphs and information, they deal with descriptions that can be observed but not measured. Quantitative is different. Most of what we do in math class is quantitative. We deal with numbers, we can measure our information. Quality versus quantity. You don't have to write every single thing down there, but as long as you have some identifying information about qualitative being about stuff you cannot measure. Or you can observe it, but you can't measure it. And think about that, like my drive. If I said, oh, if my car said I drove 55 miles an hour to get to work, I didn't drive 55 the whole way. Some areas I drove slower. Maybe I drive up the Parkway. So I drive faster on the Parkway than I do on New Hampshire. Right. So that might balance out to 55 miles an hour, but the speed does change throughout. My drive would be measured more like Mr. Dilla's, like a qualitative graph. Okay. So qualitative versus quantitative.
I did not forget. I don't still need it.
Qualitative graphs can have curved lines, ladies. That curved line indicates that the slope is not constant. It is changing, but it's not constant. So take a look here. This graph represents the number of students who are in the school cafeteria between 11 and 1. What do you notice?
Higher up. 12.
Okay, it's highest around what time?
12.
Yeah, around 12. Right, you can see that. That's when it peaks.
Like 12:30.
Okay.
No,
When does it change?
going to one. Like 12:45.
Okay, what happens around maybe 12:45?
They leave. They leave.
Okay, so we can tell that students are leaving the cafeteria. Why?
Because they're going to home.
Yeah, well, maybe not, but the
They're
line
going
itself is moving down. So in the beginning, when we first started measuring this at 11, what do we know about the cafeteria?
There are students already in there.
There are students in there. How do we know that there are students in the cafeteria at 11?
Because
It's
not
hovering.
there's no origin, like it's not going through zero.
If we had no students in the cafeteria, our value would have to start down on the x-axis. Would have to, where y is 0. Even though we don't have numbers, we can still identify where 0 would be. But that's not our graph. We actually start up here. There are students in the cafeteria. If you're thinking about a school day, what do you think happened? So we had students in the cafeteria. What do you think's happening?
Those students that were already in there are leaving.
Because some students are leaving, and then what? Think about what happens during a school day.
They're changing lunch
The
period.
bell rings. Yeah, the bell rings, and what happens?
New people come.
They come in. And then what happens at this time where it kind of
It's at its like
plateaus a little bit? What do you think's happening there?
There's a class.
that there are students like that were in there and then the new students coming in, they didn't leave yet.
Okay, so we have the most here, but that value doesn't really change a lot. What do you think's happening, Scott, during that time?
Transition. Like
Are people coming in and out
yeah.
at this point?
No, people are just coming in. I don't know.
Everybody's just
Well, it
sitting in there.
hasn't yet, right? We have, in this period of time, the number of students in the cafeteria is not really changing a ton. So the
They're
bell
eating.
rang, students came in. What do you think's happening?
They're eating.
Yeah, they're probably eating,
Nah.
right? And then, now this line moves a little bit. Think about when you're in the cafeteria. Sometimes people go to the bathroom,
Yeah.
sometimes people go meet with a teacher, but the majority of students are still in the cafeteria. And then what happens?
Everybody needs the bell ring. The bell
Yeah,
ring.
the bell probably rings, or there's some type of transition where students leave. But at the end, is the cafeteria empty?
No.
No. So these are the things that you want to identify here on your graph.
They have a
And
meeting.
when we talk about qualitative graphs, we use descriptive words like gradual, because you're going to see some changes in growth, maybe increasing or decreasing, but not all increasing values are the same. Like Mr. Dilla's drive, there was a difference between neighborhood driving, city driving, and highway driving. Right? We can't just say he started driving. Right? There's a difference between the steepness of that line. So here you'll notice that the number of students in the cafeteria builds gradually. Right? That term gradually, it says like it's not crazy, they don't run in at once, but there was a steady rate of students coming in to the cafeteria. If you're in group 1, head over now. Now, could you identify what other types of situations, as they're transitioning to iWriting, let's just turn our focus up here. 5 down. What else could be described in a qualitative graph? What kind of relationships could be described in a qualitative graph? What do you mean shifts?
Someone is waiting for a longer day.
Hold on, like, ladies, quiet down so that your classmates can share their ideas. Go ahead, Patrick.
So if someone's working a longer shift and someone else is working more equal,
Okay, so maybe just working, like the number of people working, and the hours that are passing. What else could we put in a qualitative graph? Sales is a big one. Yeah, a lot of companies will show sales, like sales in months versus down months, and they sold more, and then maybe not as much, and they sold more. Yeah, there's so much information that you can represent qualitatively. We're going to do a few examples here. In this first one here, I want you to take like 2 minutes and figure out, there's a few things that we're going to talk about. This graph represents a ball's distance from the ground. I want you to work together and describe what is happening. A few key things to focus on are where is the ball? How do you know if it's moving? How did it move? There's some information just based on the picture that you can identify must have happened to the ball for it to move or not. Let's take about 2 minutes and come up with whatever you think describes this. I'm actually going to pause the video here because I don't think we need much more beyond.